Hey guys, welcome to Tuesday's lesson of the 24th of the 3rd, 2020. Sorry this is coming out so late. I finally got all my tech working on everything that I need to work. So, I'm going to go through today's lesson. This is pretty much how everything's going to be run from the near future. So please let me know, feedback, whatever. Like it, don't like it, too hard, too easy. Probably not too easy. If it was too easy, we wouldn't be complaining. But regardless, let me know and we can try and fix it up and make it better or worse. But anyway, let's get started. So we're looking at gradients of intervals and lines. So we'll start off with the easy one, is the gradient. So the gradient of an interval. So we know the gradient is the rise over the run, as it says right there. Okay. So gradient is rise over run. So vertical rise. So if we're looking at this picture above, so the difference between the two y values. Okay, so y2 minus y1, so let's say this point Q is, I don't know, 3, 5. Okay, let's zoom in a bit. And our other point down here is, well, it's not going to be 2, let's say 1, 1. Okay, so to find the vertical rise, so the difference between this rise here is just the difference in the y's, so 5 minus 1, so it would be 4 in this case. I think I got my 3 and 5 around the wrong way, but regardless, it doesn't really matter. And then the vertical run. Okay, so vertical run is just how far from left to right does my line segment go. And to do that, all we need is the difference in the two, well, the difference of the two x in x coordinates or ordinates. So using our formula, m is equal to rise over run, the one we've learned about since year 8. We can replace our rise with our difference of our two y's over our run, which is the difference of our two x's. And that gives us this formula down here, which is P of Q is equal to y2 minus y1 over x2 minus x1. So whenever you're asked to find a gradient, we're literally just using that formula, okay? And I'll leave this stuff written on here, but yeah, that's it in a nutshell. So that's what the rest of it says. The only other bits of important information are the horizontal intervals have a gradient of 0, because the rise is always equal to 0, so if it's flat, 0 over anything is equal to 0. However, a vertical interval does not have a gradient because our run becomes 0, and you can't divide by it, we can't have a fraction of a 0, so x2 minus x1 becomes 0. We can't do that, well, we can do that, but we can't then work out the gradient using the fraction with a 0 on the bottom. So we say that the vertical interval does not exist, or does not have a gradient, because we can't have that fraction. Okay, secondly, positive and negative gradients. Positive gradient, as you read your graph from right to left, this one is going in an upwards direction. Positive gradient if it's going up. Now if it's going, so if I'm looking at from right to left and it's going down, then that is a negative gradient, or also down. Okay, pretty simple. Just read it right to left. Sorry, left to right. And that's pretty much all you need to worry about for that. Now the gradient of a line. So up here we were looking at the gradient of an interval, which is just looking at a line effectively between 2 points. The gradient of a line is looking at if the line was extended on and on and on. However, when we're looking at the gradient of a line, say this line here, for example, all you have to do is you need to just pick 1 point, 2 points, okay? Make them easy points so you can actually work it out, and then do what we did before. So m is equal to x2 minus x1 over y2 minus y1. Okay, so a gradient is going to be the same thing, except you have to pick both of those points. Okay, so maybe this one is 1, 4, and this one is 5, 8. Okay, you pick the 2 points, you find the gradients of both of them, and then, or you find the gradient of that, and it will give you the gradient of the line. Now, why we've got this extra one up here? Well, basically it's saying it doesn't matter which 2 points you pick, and it doesn't matter how far apart they are. Whichever points that you pick will always give you the same gradient, because the ratio of the rise over the run will always be the same. Okay, so if it's, if our rise is 2 and our run is 4, okay, up here the rise might be 2, but the run might be, our rise might be 1, but our run might be 2. So it's still going to give us the same fraction. 2 over 4 becomes 1 over 2, okay? And it will always give us the same fraction and the same ratio, okay? But that is to find a line. Now, for two lines to be considered parallel, if and only if they have the same gradient. Now this little thing over here says the phrase if and only if means that if the condition holds, then the lines are parallel, as in, so if they both have the same gradient, then they're parallel. But the if and only if statement means that if one way works, then you can say the other thing too. So if the gradients are the same, then the lines are parallel. However, if the lines are parallel, then the gradients are the same. It's just one of those little languagey things that you'll come to see quite a bit of. Anyway, if they have the same gradient or they are both vertical. Okay, so two lines are parallel if and only if they have the same gradient. Okay, so they are parallel if they have the same gradient. If they have the same gradient, they are parallel. Okay, all the lines are both vertical, and we explicitly say that one because, again, we don't define the gradient on a vertical line, only on a sideways boy or the other one, a diagonal of some description. That's probably really unprofessional of me to say. Anyway, here's a picture. Line 1, line 2, you do your rise, and you run for that one, you do the rise, and you run for that one, or you do, your two different points, see what they are, and you get the same thing, and happy days. If they get the same thing, they're not parallel. And that's it. Collinear points. 3 points are called collinear if they all lie on one line. So to test this, to test whether A, B, and C are collinear, test whether A, B, and B, C are parallel. Okay? So if A, B is parallel, and B, C is parallel, that means that they have the same gradient. But if A, B, and B, C, so A, B, and B, C are parallel, then the 3 points must be collinear because they are parallel passing through a common point B. So that is, if you think of it like this, here's the points A and B, and we know that they are collinear. We know that A and B are going through the same points here, okay? But then we test B and C, and we see that it has the same gradient. Well, if A and B have the same gradient, and B and C have the same gradient, then they must go on the same line, otherwise they wouldn't be in line with each other, okay? Because it would imply then, so if, let's say, if A and B do make that one line, which I cannot seem to draw, so I'll draw the line first. So if A and B are on these things, but then we find out that B and C don't have the same gradient. So let's say B and C in fact go like, not like that, in fact go like, it's really hard drawing this, go like this. Well, then we can see that if they don't have the same gradient, then they're not going to be on the same part of the line. Okay, so all you have to do is just check the gradients of A to B and B to C, which is, I think, a lot easier than the way I explained in class. Now, hard bits for today. The gradient, sorry. The gradient and the angle of inclination. So the angle of inclination of a line is the angle between the upward direction of the line and the positive direction of the x-axis. So it's basically this part in here, so between the x and the positive bit, and in here, the x and the positive bit. We know this is the positive bit because it's above the positive in the y, so like, +1, +2, etc. Okay, so we know that it's in the positive direction, that's where it is. So we're measuring, so basically we're always measuring it from the x-axis up on the right, okay? So, how do we do it? Well, if we think back to our trigonometric ratios, I can see that I've got a triangle in here, which we have as the rise, and I've also got a run in here. Now we know that the gradient is equal to rise over run, but in a right angle triangle, from this angle in here, we know that we've got, okay, so here's my rise, here's my run. So from this angle in here, we know that we've got an opposite and adjacent. Now thinking back to our tan ratios, so Remember these guys? Sokotoa. So we haven't actually done these this year, and we will be doing them later on. But we are only going to focus on this guy here, the opposite and adjacent. So that is tan. So tan alpha is equal to the opposite over the adjacent. So when we do that opposite over adjacent, okay, so my opposite in this case is a rise, and my run is and my adjacent is a run. So my tan alpha is equal to my rise over my run. So that means that alpha is equal to the inverse tan, because remember the opposite of tan is inverse tan, over the run. So tan, sine, and cosine are just functions. When you put a number in, they give you a number back out. The opposite of a opposite of a function is the inverse of that function, which we will talk about when we look at chapter 5. But just for now, we're just removing tan to the other side. Okay, now it's the exact same thing over here. Now, the only other thing I want to add is to make sure you don't forget your exact ratios for tan. So I've made a little table, or I found a little table over here. Here are the tan ratios over here. These are the ones that we're focusing on. So it's 0 degrees, it's 0. If it's 30, it's 1 on root 3. 45 is 1. 60 degrees is root 3. And 90 degrees is not defined. We will talk more about that when we do the trig topic. You don't have to remember these drastically, but if they do pop up in the exercise, just pop back onto this page and have a look and see what those are. However, we won't be concerned about that too much. Anyway, so the two diagrams above show that the lines positive gradients have an acute angle. So if you have a look at the first, I need to turn my steam off. If we have our first one, our gradient for this one, it's going up from left to right, so it's positive, and the angle on the inside is acute. Now, if you have a look at this one, we've got our negative gradients going down. So as you can see, our angle from our x to the positive part of our line is obviously obtuse. Okay, but you still use this formula to do it the same way. I'll show you how the obtuse one works though later in the example. Now, last thing that we need to talk about is perpendicular lines. So a perpendicular line is two lines are considered perpendicular, or that they meet at 90 degrees, if and only if. So this is this statement again. M1, so the gradient of the first line times the gradient of the second line is equal to -1. So where M1 and M2 are the gradients of two lines, or alternatively, one is vertical and the other is horizontal. So one gradient is not defined, whereas the other gradient is equal to 0. So the condition M1 times M2 is equal to -1 can also be written as M2 is equal to -1 over M1, or in other words, the negative reciprocal of the other gradient. Okay, and we'll look at that more in a moment. But two lines perpendicular if and only if M1 times M2 is equal to -1. However, if M1 times M2 is equal to -1, then those lines must be perpendicular. So it's always important to know that you can go from one to the other and back with no issues whatsoever. So let's look at the updated examples for this one here. Those of you who were in the class today would realize how much of a cluster stuff this stuff was. I have changed the numbers. No, I haven't. Why haven't I changed the numbers? Because I'm an idiot. That is why I've done them on my big one, not my small one. So I'm going to quickly change that to -2. Apparently not. -2. Okay, so let's do this question. Given the 4 points, A is equal to 0, 1, B is equal to 4, 2, C is equal to -1, -2, and D is equal to 3, -1. Show that the quadrilateral ABCD is a parallelogram with AB parallel to CD and AC parallel to BD. Now, the first thing I'm always going to tell you whenever you're doing one of these geometrical problems with points is to graph this thing. Just do a quick sketch. It doesn't have to be too extravagant. It's just to see what we've got and how, or what it looks like, what this thing is going to kind of look like. So I'm on the side, I'm going to draw up a quick little doodle. Now my points are 0, 1, so that's about here. Okay, so look, I'm not even, like, this is not official, it's just a way for me, whoop, not C, it's actually a B. This is just a way for me to see what this shape is actually looking like and what do I need to do. So C is -1, -2, so across the -1 down to -2, so it's about here, that's C. And D is 3, -1, so 3, so it's about here. Now, if we put these things together, we can see that we have got a parallelogram. Now, to prove that it's a parallelogram, we need to show that this segment and this segment are parallel, and that this segment and this segment are parallel, okay? In fact, I will actually draw these out. Goodbye. I will draw these arrows going the other way because we can see just from our picture that both of our gradients will be positive in this case, okay? So with AB parallel to CD, so the two lines just mean parallel, two lines that are parallel look like they are parallel, and AC is parallel to BD. So we'll start with finding the gradients, because if we want to show that these things are parallel, we need to look at their gradients. If their gradients are the same, then they're parallel. So I need to look at AB, the gradient of AB. So M of A, get rid of that, and make a little a and a little b. So the gradient of AB, or MAB. So we know the formula from the other side was y2 minus y1 over x2 minus x1. It's just the difference of the y coordinates over the difference of the x. So back up here, I'm doing a and b, so I'll go y2, x2, y1, x1, okay? And I'm going to put these on here, like thus. So we're going to go 4 minus y1, so that's 1 over, sorry, why did I do 4? I am silly. It should be 2 minus 1 over 4 minus 0. Okay, now putting this into a calculator because we need our help. No, not really. I'm just tricking. 2 minus 1 is equal to 1 over 4 minus 0, which is equal to 4. So the gradient of MAB, the gradient of AB is equal to a quarter. Now, for this to be parallel, we're hoping that CD is also parallel. So I'm going to be doing CD now. So I'm going to call C x1, y1, and D x2, y2. And I'm going to go to gradient of CD is equal to y2 minus y1 over x2 minus x1 is equal to y2, which is -1, minus y1, which is -2. So -1 minus -2 over x2, which is 3, minus -1. Now, it is important that when you're labeling your x and your y's, you make sure that they're in the same order. So y2, y1, x2, x1. So this 2 goes first before the 1. It doesn't matter if you call this one here x2 and this one here x1. It will work out to give you the same answer, so you don't need to stress about that. But you just need to make sure that the 2's go first and the 1's go second, or alternatively the 1's go first and the 2 go second. -1 minus -2 is equal to 1. And 3 minus -1 is equal to 4. And there we go. So we get that AB is parallel, or therefore AB is parallel to CD. And that is that's half of done. So we've shown that 2 of the sides are parallel. Now we've got to do AC and BD. So AC and BD. So I'm going to go back over here. I'm going to go x1, y1, x2, y2. So M of AC is equal to y2 minus y1 over x2 minus x1. Now I'm just going to do that every single time, so I demonstrate that I understand that I'm finding the gradient. y2 minus y1, so that's -2 minus 1 over -1 minus 0. -2 minus 1 is -3 over -1, so that is just equal to 3. Okay, and if we have a look at our picture 2, we can see that we're doing AC, and AC is over here, and it's kind of steep. Okay, so back over here, we've done M of AC. Now we're going to do M of BD. So that is, let's remove these little guys here. And we're going to put in our x2, y2, and x1, y1. Okay, so doing our formula, y2 minus y1 over x2 minus x1 is equal to 3 minus 4 over, you can already see it's negative 1, x2 is, hang on, why did I pick 3 again? I seem to be, okay, negative 1 over minus 2, which is looking a bit better, and an x2, which is 3 over minus x1, which is 4, which is a lot better. So move this guy down a bit. So we've got minus 1 minus 2, which is equal to negative 3, over 3 minus 4, which is negative 1. So therefore, that is equal to 3 as well, which is the same as before. So therefore, AC is parallel to BT. Okay, and then we can finish up our thing by saying, therefore, as we have two pairs of parallel lines, then the quadrilateral, or just quad, of A, B, C, D must be a parallelogram. Done. Okay, so it's quite a bit of working out for that one, but nothing too tricky. It's just applying a formula for, well, not applying a formula, but it's just, well, it is. It's just applying the formula for the gradient 4 times and checking whether or not you understand that for lines to be parallel, they have to have the same gradients. And that's all we're doing. We're just checking whether or not the gradients are the same for that. Okay, so that's pretty good. I'm just going to rub this top bit out from here. Okay, and we are going to get stuck into example number 2. Okay, test whether the 3 points, 1, 0, B, 2, negative 2, and C, 5, negative 8. Looking back over to my notes on the side, I remember that these are correct, so that's all good. Now, what I need to do is I need to check to make sure these 3 points are collinear. So that is, all I need to do is check that A and B, and then B and C, and because we've got that common point of B with gradients the same, if the gradients are the same, then these lines must be collinear. So, let's start with AB. So AB, I'm literally just applying the gradient formula again. So AB is equal to x2, no, we don't want that. We want y2 minus y1 over x2 minus x1, okay? So using this formula, we're going to go negative 2 minus 0 over 2 minus 1. And that gives me negative 2 over 1, which is equal to negative 2. Now, what we're going to do next is we're going to check BC. Now, if this has the same gradient, then it just falls out the fact that they must be on the same line, okay? Again, with that common point, if we have this common point here, okay, for this point to be the same as that one here, they have to share that same gradient going across like that, okay? Which is, again, much easier than the method I showed in class today, so whoopsie doodles. Okay. So, well, not harder because you're going to be doing that tomorrow anyway, but regardless, let's do it this way. So BC, we're going to go, so we've got our our new formula, and we're going to write down our new points. Doesn't matter which one you call x1, and just do the same thing again. Doesn't matter which one you call x1, y1, x2, y2, it will work both the same way. So let's do it like this. So we'll start with y2, so we've got minus 8 minus y1, which is negative 2, over 5 minus 2, okay? So negative 8 minus minus 2 becomes negative 6 over 5 minus 2, which is 3, and that is just equal to negative 2. So as AB and BC have the same gradient, with a common point B, then A, B, C must be I think that's one word, not two. Damn it. Collinear. Okay. So pretty straightforward. Just check both the gradients, see if they're the same, and because we've used the same point in both of them, then they must be in that row. Now we can double check this by using everyone's favorite graphing calculator, Desmos. That was just me checking the points for that example. So if I put these ones in, go 1, 0, okay, there he is up here on that little point there. I'm going to change that projector mode so we can see it better. 1, 0, we go 2, negative 2, and we're going to go 5, comma, negative 8, 89, and if we have a look, so there's the two of the points. Whoops, that was the wrong one. Goodbye. That was those two, and if I scroll down, we will be able to see that third one there. Okay, so I don't know what the equation of the line is, but they do look like they are in the same line. In fact, I think I might be able to work out the line. It might be minus 2x plus 1 plus 2. There we go. And in fact, they are in a line. So there we go. Collinear. Beautiful. Now, that's example 2. Let's move on to our second last example, example 3. Now, this is another one where I'd recommend drawing a picture just to get your head around what we're actually doing. So part A says, given the points 3, 5, 6, 0, and 0, which is the origin. So that's why we call it the point O. So whenever we refer to the point O, we're usually referring to the point origin. But regardless, we're going to continue. Find the angles of inclination and the intervals AB of, hang on, let me say that. Find the angles of inclination of the intervals AB and AO. And then we're going to ask, or we've been asked to find what sort of triangle that is. So let's start off by drawing the picture, just to get our heads around what we're trying to do. Okay. So 3, 5 is, well, let's start with the easy one. So 0, 0. So that's the point O. Point B is 1, 2, 3, 4, 5, 6 away at 6, 0, and that's the point B. And the point A is 1, 2, 3, 1, 2, 3, 4, 5. Okay, and we put that on, we put an A there, and we can connect them up because we know we're making a triangle. Cool thing about triangle is that the lines are actually straight, so try to make them as straight as possible. Again, without a ruler is probably best, but you don't need to, just as long as they're relatively straight. Okay, there it is. Looking at that, can't quite tell because my sketch is not the best, but judging from that, I would suspect that it's probably isosceles. So to check if it's isosceles, we should have angles that are the same, and we'll have a look in a moment and see if that's true. However, the first thing we've been asked to do is to find the angles of inclination. So we'll start with AO, which is an easy one, because it's this one on the inside here, okay? And we'll call this one alpha, because we like alpha. We like the Greek letters for our angles. So to do this, I need the rise and the run of this point here, or the gradient. So m is equal to, so we know what the point is. We know what point A is, so y2 minus y1 over x2 minus x1. And we know what point O is, because it's just the origin. So let me put my points on there. We're going to go, I'm going to make A number 2. Whoop, that's A, not that is x2, y2. And I'll make this one x1, y1. So when I put these in, you'll see why in a sec. y2 minus y1 is 5 minus 0 over x2 minus x1, which is 3 minus 0. So the gradient of that is 5 over 3. Okay, so we know that's the gradient. However, we also know for the angle of inclination that tan of alpha is just equal to what the gradient is. In other words, because we know from before, well, sorry, let me rephrase that. We know tan of alpha is equal to x2 minus, not x2, y2 minus y1 over x2 minus x1. And we know that this is just equal to m. So therefore, tan of alpha is equal to what my gradient is. So that's why we worked out the gradient. So that must mean that tan of alpha is equal to 5 on 3. And so using my inverse tan, I can work out that alpha must be tan of -1. Now, we're going to put this in our calculator, work out what alpha is, and so we go doot, 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 and we work out that tan of -1 of 5 over 3, and so remember you have to have shift and tan on your calculator. So to do that, we get 59 degrees, rounded to the nearest degree. Okay, so that's that one done. For our second one, we need to find the angle of inclination, which is this bit here. So this is for AO, I'll add. Now we're going to do AB. So there's AB. So we need to find the gradient bit to begin with. Okay, and we're going to be using A and B this time. So not A and O, A and B. So I'll put X1, Y1 there for those ones, and X2, Y2 can stay on the A. So using my gradient formula, y2 minus y1 over x2 minus x1 is equal to, so we're going to go y2, which is 5, minus 0 over x1, x2, which is 3, minus 6. Okay, so working that out, we get 5 over -3, which is just equal to -5 on 3. So my gradient for my second one is 5, 3, but it's negative. So to work out the gradient, we're going to do the same thing. We're going to go tan theta, or well, actually, we need to give it a name. That's an alpha, by the way, not a theta. Let's call it beta, because it's a beta. Tan of beta is equal to, so we know it's equal to m. So that means that tan of beta is equal to -5 on 3, or -5 of 3, which means that beta is equal to tan of -1 of -5 on 3, or -5 of 3. So we put that into our calculator, and what we get is -59 degrees and 2 minutes like we did with the other one. Now you might be saying to yourself, beauty, that's awesome. We've got two things, but you may notice one thing in particular, which is jumping out at me, especially that we can't really have for an angle, and that is that it is negative. We can't have a negative degree on our angle. So to work out what beta is, because it's obtuse, so I'm not going to use a beta, I'm going to use B cos. Beta is obtuse. What we're going to do is we're going to add 180 to -59 degrees. Now the reason we're going to add that is because it's going to give me a negative number. So we do 180 plus -59, and that is equal to 100 and something degrees. I'm going to say 121 degrees. Because remember, it has to add up to 180. So, no, it should be 111 degrees. 111 degrees. Because if I add 59 to that, it gives me... The 9 gives me to 20, and then the 5 gives me 101 degrees. Am I really... Geez, I can't... use a calculator, friends. Use a calculator. It will help you so much more. 180 plus 59 plus -59. I just can't even today. 180 minus 59. There you go, 121. I was right the first time. I don't know why I was doubting myself. Anyway, so angle beta. So therefore, beta is equal to 121 degrees. So that's the outside. So that's the angle of inclination. So we know it's obtuse because it's the outside one. So back over here on our picture, we know it's obtuse because it's the outside one. That's the one that I need to do. Okay. Now, what sort of triangle is ABO? So ABO, so this is part B. So triangle ABO is what and why? So we know what the inside of AOB is, so that's where my alpha is. We know what the outside of ABO is. What we can work out is the inside. Now, do we remember how to do this? Do we remember exterior angle sums for a triangle? Exterior angle sum is that the outside angle of a triangle and the inside angle add to 180 degrees. So 180 degrees minus my beta, which is 121 degrees, gives me 59 degrees, just like we got with the thing. So because we have two angles of 59 degrees, triangle ABO must be isosceles. So ABO is isosceles. Now, typically, you wouldn't have to explain all that. Okay, you could just do 180 minus 121 is equal to 59, and then because we have the two, therefore triangle. Okay, so that's it for that one. Pretty cool. I like these geometry problems because they actually have to make you think, how can I prove this thing by only using stuff that I know? And that is one of the ways. So, with that being said, let's move on to our final example. Now, I am judging that this was another one that I got wrong, and I'm presuming that I haven't changed the numbers yet again. So, excuse me, can you actually do something I want you to? Thank you. So if you ask nicely, electronics especially, usually do what you say. Let me just change two of these numbers, and this will make it work, I promise. I think. Let's find out. All right. I'm sure it'll work. Okay, example 4. Show that the diagonals of the quadrilateral ABCD meet at 90 degrees, where the vertices A, B, C, and D are there. Don't have to read them out to you. I'm sure you can see that, but no. A is equal to 5, -1, B is 9, -4, C is 2, -5, and D is 6, -8. There you go, I did it. So I don't want to hear any comments saying that I don't help, because I try my best. Let's draw these points and see what type of shape we've got. Now, if they meet at 90 degrees, means that the two diagonals must be something special. It also means that this shape has to be a specific type of shape. And if you guessed a square, go you. You did it. So, doing this now, we're going to find our next bit. So, let's go 5, -1, so that's about here. So that's A. 9, -4 is about here. We'll call that B. 2, -5 is about here. We'll call it C. And 6, -8 is about here. And if you have a look at that, if I put these together, hopefully you can see that I've got what resembles kind of a square. Now, it's not going to be perfect, but you can kind of say, oh yeah, it kind of looks like a square. Okay, so let's dissect this question a bit further. Show that the diagonals of the quadrilateral ABCD meet at 90 degrees. Okay, so in the diagonals, so here's my quadrilateral with the dots. Well, actually, I'll make them... Oh, no, I won't. Here's my thing with the dots. The diagonals are the ones that cross over. So what I need to do is I need to show that these meet at 90 degrees. To show that something meets at 90 degrees, then the lines must be something. If you guessed perpendicular, well done you. You got the correct answer. If you can read that horrible, horrible handwriting. But yeah, so the diagonals of the quadrilateral meet at 90 degrees. That means that diagonals must be perpendicular. If I'm looking for perpendicular, I am looking for something in particular. I am looking for the gradients. Yes, you got it. Well done, you. If you're following along at home and you answered gradient, buy something to celebrate. Anyway, let's continue. So we're looking for AD and BC. So the gradient, so M of AD, is equal to y2 minus y1 over x2 minus x1. So I need A and D in this case. We're going to go x1, y1, and x2, y2. And I did xy for some unknown reason, y2, like that. Okay, so putting these points in, what do we go? We go -8 minus -1 over sorry, I was just thinking for a sec. No, that's right. Let's continue. -8 minus -1 over x2, which is 6 minus 5. Okay, so putting that in, we get -8 minus -1, so that becomes a plus. So -8 plus 1 is -7 over 1. So my gradient for AD is equal to -7. Okay, now we're going to do our gradient. So we only have to do the 2 this time, which is good. We're going to do a gradient of BC. So my gradient of BC is equal to y2 minus y1 over x2 minus x1. I want you guys to write this down so much that you're going to get sick of it and you're going to remember it forever, because we actually need this formula later on to prove, well, not to make a new form for an equation. Anyhow, let's put some values in. We've got B and C, so I'll go x1, y1, and x2, y2. So putting those in, we're going to go y2 is equal to -5 minus y1, which is -4, over x2, which is 2 minus 9. So -5 minus -4 is -1 over 2 minus 9, which is -7. But we know that -1 divided by -7 gives us a gradient of 1 over 7. Okay, so for these two lines to be perpendicular, so for AD to be perpendicular, that symbol just means perpendicular, to BC, then M1 times M2 must be equal to -1. So if we go, so -7 times 1 on 7 is equal to, well, -7 times, so it's just -7 on 7, which is equal to -1. So therefore, AD must be perpendicular to BC, and thus meet at right angles. And we're done. So quite a bit to take in for this one today. Take it step by step. Okay, actually think to yourself, okay, what did he do next? Okay, and I'm hoping I've explained everything on the way. It does get tricky. You know, this is not easy stuff. Like, I mean, like, it's not too bad, this stuff, but maths in general, it's not meant to be easy. If it was easy, everyone would be a mathematician. There's a reason why you guys are doing what you're doing. It's because you do it well. Keep up the good work, and I'll see you in the future. Goodbye. Oh, make sure you hit like and subscribe and thumbs up and hit the bell. Don't forget to hit the bell. If you don't hit the bell, then I lose my money.